So far, we have investigated examples of circular motion on or near the surface of the Earth. Did some labs as well. Here are a few vocabulary that we will encounter as we talk about circular motion involving planets, satellites, and the moon. And we have a gravitational field, which is lowercase g, coincidentally the same as the free fall acceleration value of 9.8 meter per second squared, or 9.8 newton per kilogram. Gravitational force, another vocabulary, which is determined by the gravitational field and the mass of the object. So the M here would stand for the gravitational mass. There's another term that they might use in your AP Physics 1 exam, which is called the inertial mass. So there's a difference between gravitational mass and inertial mass. Gravitational mass is due to the gravitational field. Inertial mass is determined in terms of the acceleration, or would indicate how the object would respond its acceleration to the net force. So just to take note of that. Another one is Newton's gravitational constant, which is the uppercase g. So be careful. We now have 2g here, the lowercase g, which is the gravitational field, and the uppercase g, which is the gravitational constant. So Newton's laws of universal gravitation, or LUG. So besides developing the 3 laws of motion, he was curious on how about the motion of planets and the moon. He was curious about that. According to legend, he was sitting under an apple tree and he asked a question about gravity. So if gravity acts on all objects, no matter where you are on Earth, may you be on top of a tree, right below the surface, or on top of Mount Everest, you will experience gravity. And that always tend to force you to go towards the center. So if this acts on objects near Earth, what about the moon, which technically is within the field of Earth's gravitation? And he developed the great law on universal gravitation. So that's what we're going to look into. So there are a few properties in terms of the law of universal gravitation. So one of this property is that the gravitational force is dependent on this inverse square of the radius of the 2 objects from its center. So mathematically is shown here. Now we know that, so he figured out that if the objects that fall towards the Earth is acted upon by a force of gravitation, then that distance, the square of the distance between the object, is something that is of a concern. So another relationship that Isaac Newton realized, that the force of gravity on an object does not only depend on the distance, but also on the object's mass. So in fact, it is directly proportional. It is directly proportional to the masses of the 2 objects. So given the 2 relationship that Isaac Newton was able to see, and we combine all these factors, and also using the value of g, which is the value 6.67 times 10 raised to negative 11 Newton meter squared per kilogram squared, which is a universal constant, true for all planetary object that revolves around a sun. Although this is a law, that doesn't mean that this applies to every physical phenomenon that involves circular motion. This is only true if the object is spherical symmetry, is that the distance between those is much bigger than the size of the object involved. This is something that we can look at for planetary objects. This was Henry Cavendish apparatus in determining the value of G. So with the law of universal gravitation, we probably would notice that as the mass of these two objects that are experiencing gravitational force increase, the gravitational force also increases given if the radius stays the same and the constant stays the same. Now what happens if the object increase its distance away given the same mass? What happens to the gravitational force? The gravitational force tends to decrease as it moves farther away from each other, and that gives a concept. Say for example, two objects whose having initially have the same mass. Now we double the masses and we quadruple the separation. So what is the magnitude of the gravitational force? Okay, so the answer would be 1/4. How does the third law apply on this law of universal gravitation? So if we know that one object exerts a gravitational pull on the other object therefore will exert an equal but opposite gravitational force. But come to think of it, so if the Earth exerts a gravitational force against a falling apple, why not the Earth moves towards the apple? Why is it that we only see the apple accelerating towards the Earth? And that is true for any object. So why is it that you sitting next to your classmate doesn't experience that gravitational pull towards each other? Why is that? Remember the second law. So that says that the acceleration is directly proportional to the applied net force. So given, say that the Earth force on the apple is our net force, which equals by third law on the force applied by the apple and the Earth. Looking at the masses of both, so you compare the mass of the Earth with the mass of the apple, you will definitely see a big difference in here. So given the mass of the Earth, its acceleration will be too small to be noticed. And given the mass of the apple compared to the Earth, now its acceleration is more noticeable than the acceleration of the Earth. And there is no device to really see how the Earth's motion as the apple fall towards it or pull towards each other. And that's how we see the third law applies to it. Also about around 1600, more than half a century before Isaac Newton developed his laws of universal gravitation, there was this German astronomer who was able to study the planets, and his name was Johann Kepler. He worked out a detailed description and developed what he called the three laws, the Kepler's laws on planetary motion. So you have the first law as stated, the second law, and the third law. So Isaac Newton was able to show that Kepler's law could be derived mathematically from his law on universal gravitation and the three laws of motion. And Newton was able to integrate all these results of earlier scientists, and this is what we speak as Newton's synthesis of the different laws. That includes his two laws, the LUG and the three laws of motion. However, the Kepler's laws on planetary motion doesn't always indicate a precise measurement because there are slight deviation as the objects, the planets, move around an elliptical orbit, and these are called perturbations. That's shown in the planet Saturn and the planet Uranus. So what about satellite motion? So the best example is our Earth's natural satellite, which is the moon. So the moon orbits Earth due to the force of gravity that provides the needed radial acceleration. So a satellite is an object that is smaller uh, than the object to where it orbits, and that's how we define it. And it's now commonplace that we have different artificial satellites, but what's keeping this satellite up, and does it follows the laws of universal gravitation? Um, the answer to the question on what is keeping it up is technically it's very high speed. So in order for satellites to be able to move in near circular orbit, they must travel a certain speed, and this satellite must always stay above the same point on Earth. So technically they can't be if they are way beyond 0 degrees. So most of them are launched at the equator, and these are called geostationary satellites or geosynchronous satellites, because they have to move fast within a 24-hour period. You probably notice your satellite dish, the directivity dish points at one direction. It usually points south. I'm not very specific to what the actual direction is. I can't remember. I was talking to this satellite guy way back and I can't remember. So if you happen to, you can ask them. They use a certain device to actually measure the actual angle before they set up the dish on the top of your roof or anywhere else. So those point to a particular location. So those satellites must be at exact same point. Because why on the equator? Because the center of the satellite orbits always point at the center of the Earth. So it's not possible if it is any place on Earth beyond the equator, which is 0 degree. So how do scientists, engineers are able to launch satellites? How do they know how far they are? So we could apply the second law in here. Applying the second law, so the object is going to be moving in a circular path due to the radial force by the Earth, and it will accelerate radially due to that. So applying that the force of Earth is also the law on universal gravitation. I'm just going to use uppercase here and small for the satellite, radius squared, and the mass of the satellite, and knowing acceleration from our circular motion is equal to v squared over r. And simplifying this equation, I could arrive at an equation, so I can cancel out the mass of the satellite here, which is irrelevant in the equation for finding the velocity. I would have g mass of Earth over their separation. So this is how I can determine, that's how can I determine the velocity. From here also I could determine how far would that be from relative to the Earth's center. That's how you determine motion of satellites and how far they should be launched from the center of the Earth. So one last concept in terms of circular motion is the term weightlessness. So is this actually true? So if we say weightlessness, that means the object, or particularly the object's gravitational field or the gravity really disappears? We don't think so, right? So more importantly, we can refer to this as what we call apparent. So apparent weightlessness. So that might be a more appropriate word. So we may say that we don't actually have, but gravity is always there. It does exist, and that is, of course, if the object is really, really far from Earth, or any object that shows gravitational pull. But in terms of this, we take note that the object is still close to the planet or to the Earth, and people experience even those that are in the International Space Station. It's kind of like a free fall experience, a free falling body. But let's not go beyond that. Let's just look at this elevator scenario here, which is technically is not a very strange, but it is a feeling of weightlessness. So we look at A, we see that the object is moving at a constant rate, constant speed, therefore it's not accelerating. So we could see here that the weight on the scale is equal to the force of gravity. Now the object starts to go up. So what do we notice in here? So since its acceleration is pointed up, which is positive, what happens to the weight compared to the force of gravity of the object? So did it decrease or did it increase? So we could see here that it did. Now what happens if this cable snaps, which hopefully doesn't happen where you're in a 100th floor of the elevator, and we would notice that there is no other force acting on the object but the force of gravity, and the acceleration becomes equal to the value of g, which is gonna make you feel like you're on free fall, which is an apparent weightlessness. So all of us experience, we see this in sports, we see this when we ride the elevator, and here are great examples of apparent weightlessness. So all these examples experience relatively being weightless, but then again, this situation are examples of free fall or apparent weightlessness on Earth at brief moments.